Today I'm going to talk about a classifier, and maybe more importantly, machine learning classification workflow that we use in Rafael. My collaborator in this work is Amir Navot, and in Rafael, in Rafael's image processing and computer vision department, we lead the activity of developing and incorporating tools into as mission-critical components of larger systems. And before I start, I have this. Before I start, let me show you a short clip that I found on YouTube that I think gives a good demonstration for the motivation to this talk. So let's play this.
Close your eyes and just fall down, okay? Don't worry.
Okay, then Lauren's going to catch you.
Close your eyes. Okay.
Okay, it's called the trust fall. Okay, trust fall. Ready, set, go.
So, I think this really demonstrates the importance of being very specific with your instructions. And what's true of people is also true of, maybe more true of machine learning algorithms. Because with machine learning algorithms, we do something basically very simple. We give them an objective function. It's usually the loss, the average loss on the training set plus some regularization term. And we tell them, minimize this, and they do that. And they do that very single-mindedly. And they can use the features that we give them in very strange ways, and sometimes things, and they can do this in ways that we didn't think of before, and things can go wrong. And one way that things can go wrong is well known to most of us. It's the dreaded overfit. Right? And this is something that worried the machine learning community for a long time, and still does. But I'm going to discuss other causes for worry and how, in our work, we try to overcome them. So, in the title it says mission critical. So what does mission critical means? Well, it basically very simply means this. We have a classifier. It's part of a system. If the classifier makes a classification error, this means that the mission failed. It's as simple as that. Classification error means the failure of a mission. If it's a test, then it can be just very embarrassing. If it's an operational system in an operational scenario, this can mean the loss of lives, right? So this is something very serious. So the challenges of mission-critical applications of machine learning are primarily due to one primary factor. And this is that it's hard and sometimes impossible to test the classifier in real operational scenarios, and this is due to this is inherent to these problems, because to create a real operational scenario means that you put property and lives in danger, right? So you can't really test the system in real scenarios, or it's very expensive or very difficult, and you try to simulate these scenarios, and each way to simulate such a scenario brings with it some kind of a bias into the training data. And what's worse still is that this bias is not known. So it's all the methods that try to compensate for bias in the training data, the conventional methods assume that the bias is known, but in our case, the bias is not known. One redeeming feature of our problem, of these kind of problems, is that typically we have a very good understanding of the features. And I'll get into that later. So, the project that we were clear to describe in this conference is a project called SIS Porter. It's a naval IRST system, IRST standing for infrared search and track. And this means that this system sits on a vessel, on a ship, like this one. And its task is basically to detect threats to the vessel and also to provide it with situational awareness. And these threats range from attack aircrafts, guided missiles, sea skimming, cruise missiles, small attack crafts, etc. So there are quite a few types of threats that this system has to handle. The most challenging threat is probably sea skimming missiles. And the reason for that is that they are very fast. They are launched typically from beyond the horizon, something like tens of kilometers from the ship. They rise above the horizon about 25 to 30 kilometers from the ship. It takes them about 30 to 60 seconds to hit the ship. And their trajectory is very close to the horizon, less than 1 milliradian above the horizon, which means that they comprise very faint stationary point targets. And if you look at this picture here, which is a slice from, I didn't mention, this is an electro-optical system, right? There's a bunch of cameras looking at a 360 degrees circle around the ship, and they try to detect those threats. So this is a snapshot, and you can see here a ship, but this is not what we're trying to detect here. This is what we're trying to detect, this little thing here, okay? So this is what makes it so difficult, and just to impress you a bit with this kind of missiles, I found a clip on, another clip on YouTube, which shows the launching sequence of a Russian missile. It's quite impressive, really, to look at it.
Есть красота. Легла на боевой. Все. Есть. Носовик пошел.
Why do you do that? Okay. So that's the threat. And the algorithmic workflow that we use in the system, the machine vision part of it at least, is that we get a video input. There's a low-level detection algorithm that basically goes through all the pixels in all the cameras in each frame, and we're talking about a video stream of about 50 frames per second. So in this sense, this is really big data, or at least big throughput, high throughput. So this model here detects all suspicious pixels and bunches them up into blobs. Then these blobs are used to generate temporal tracks in the image. And these tracks are then transferred into this classification block, where this is where machine learning comes into play, right? Because this is our classifier. It classifies tracks. It assigns to each track a grade. And then there's a very simple logical step in which the grade is used to decide whether to start reporting on a track, and if we are reporting on a track, whether to continue reporting or stop reporting. Okay, so this is where machine learning comes into play. I have maybe one or two more clips that should be interesting. This is two kite surfers on a beach not far from here. So you can see the kites are pretty visible, but you see that the system also detects the surfers themselves. And here is another one where you can see that we reject, damn. Okay. So these are a few ships somewhere, and there's a lot of glitter here on the sea, and this generates a lot of suspicious tracks, but the classifier rejects them. Okay? And it's very important that a system like this generates very few, if any, false alarms, because if it generates a lot of false alarms, nobody's going to use it. They're going to turn it off, and end of story. Okay, so that's the basic architecture. So what I'm trying to, maybe the takeaway message from this talk, I think should be that in mission-critical applications of machine learning, the conventional workflow, at least for offline learning, that is development time learning, of machine learning is inadequate. And this is the conventional workflow, right? You collect lots of data, you label it, or at least some of it. You choose and train a classifier. You validate it, let's say by cross-validation. You repeat that several times with a different classifier. At the end, you pick the best performing one, and you deploy it in your system, right? So this is the conventional machine learning workflow. And I'm going to claim that this workflow is inadequate for our purposes. So what's wrong with that? Well, the training data is biased. I said that before. We have all sorts of ways to simulate the real operational scenario. Each of them comes with its own type of bias, and the bias is unknown. And we cannot simply trust the data and hope for the best, not even when it's big data. And in this respect, we're probably different from all the internet applications of machine learning. The data is not trustworthy, not completely. Okay, we have to be very careful in using the data. But we do know a lot about our features. Usually the features are very high-level features representing physical quantities that we have a good understanding of. And we want to leverage that. We want to use our familiarity with the features to control the training process, the learning process. And validation must go beyond cross-validation, because the held-out data that we would use in a conventional cross-validation procedure is just as biased as the training data. Okay? We don't have some oracle to provide us with unbiased data to test our system with. So, with this in mind, there are a few things that we would like our classifier to be capable of delivering. First, we want the classifier to be transparent. And by transparency, I mean that we should be able to look into the inner working of the classifier and understand how it makes its decisions. So this really means that the classifier has to be pretty simple. It has to be interpretable, and this means that we should be able the classifier should be able to provide explanations for its decisions. And this should preferably be in terms of the input features, the physical quantities, that explanations that we can, that a layman or a manager, for that matter, would understand. Okay, these right? We don't want just explanations that the engineers would understand. We want the classifier to be malleable. That means that we want to be able to inject into the classifier in the training process our prior knowledge about the problem, about the features. Okay, we want to be able to mold it somehow. We want the classifier to be discriminative and probabilistic. Discriminative because we don't want to model the joint distribution of the inputs and the labels, because this may cause us to have to handle two sources of bias, the bias in py of x and the bias in p of x, right? This would be a generative model would have to consider both these terms. Discriminative models only have to consider this one term, so if there's no bias here, at least this helps us a bit. And we want them to be, we want the output of the classifier to be probabilistic, because probability is a very useful common language with other parts of the system, right? We're only a small part of a larger system. We want to be able to communicate with other parts of the system. Just saying, using a classifier that says yes or no is not informative enough. We want to be able to provide probabilities, and we want to be able to handle a lot of data, so the classifier has to be efficiently learnable, and we want our classifier to be able to handle missing values. Okay, so here's what we propose as a classifier that satisfies all these desiderata. So we call this classifier factored logistic regression, and the basic idea is quite simple, really. So the xj's are the input features, and what we do for each input feature, we learn a separate logistic regression model, which basically models the log odds, right? The logarithm of the probability of the sample to belong to the positive class divided by its probability to belong to the negative class. And we model each component as a linear combination of basis function. This is standard for logistic regression. So this is a shorthand way to write it. And what's important to understand here is that this function is linear in the parameters. It's not linear in the inputs. It can be arbitrarily complex and non-linear in the inputs, but it's linear in the parameters. So this, when we get down to solving it, is a very simple one-dimensional convex optimization problem which can be solved very efficiently, very quickly, millions of examples in a matter of seconds. Okay. So now we have for each feature basically a one-dimensional classifier. How do we combine these into one classifier? Well, the idea is to apply some monotonically increasing function of the individual, these individual model log odds. And one example to demonstrate it would be to simply add them up, to sum them, right? You have, for each feature, you have a one-dimensional classifier, and you simply add them up, and you add some constant which is independent of the features. And when it comes to performing the classification, you simply threshold the overall log odds. So this is how classification is performed. That's the log odds. And logistic regression has quite a few advantages. As I said before, it's linear in the parameters. It's a convex optimization problem, which means that there are efficient algorithms for learning the maximum likelihood, the maximum posteriori, and the full Bayesian solutions. And it provides a discriminative and classifier with a probabilistic output. So already we satisfied quite a few of the desiderata. So I said that we want to somehow be able to use our prior knowledge in molding the classifier. So I'm going to give an example using a familiar data set, which is the Titanic data set. So the task here is basically to take the passengers of the Titanic, the passengers and the crew, and to classify them into those who survived and those who didn't. And there are just three features. There's age, 0 being child, 1 being adult, gender, 0 being female, 1 being male, and class of travel, 1 to 3, with 4 being the crew members. And we have some prior knowledge, right? I mean, we can look up the Wikipedia article on Titanic and see that it sank quite slowly. There were not enough lifeboats for everybody, so the crew had to implement a women and children first policy. And we don't have to look into Wikipedia that it's, to know that it's not bad to travel in class. And the way we use that is simply by enforcing monotonicity constraints on each one of the component models, right? So being a child is better than being an adult. Being a female is better than being a male. And a higher class is better than a lower class, right? And these are constraints that, well, let me skip on that. So this is what happens when we really do it. This is an actual screenshot, almost a screenshot of one of our tools. So here we display the model learned for the class feature, for the age feature, and for the gender feature. The dashed line is what happens when we train on the entire data set. So the dashed line is what really the complete data set tells us. So it agrees with our intuition, right? You see the dashed line for the class, it's monotonically decreasing, more or less. For the age, it's the same, and for the gender, it's the same. They're all monotonically decreasing. And now we took a small subset of just 20 examples, and because it's a small subset, it's therefore biased. So this is our way to simulate bias. And we trained FLR without any constraints, and we basically got nonsense, at least for the class and for the age features, right? This is the black line. So we have something very strange for the class. Second class is better than first class, and etc. And for the age, it's even worse. It's better to be an adult than being a child. And for the gender, it's okay. And then we trained the constrained version of FLR, and you can see that we got rid of most of these artifacts. So this is the black line, right? That's the constraint. So you can see that it's not as good as learning the full data, but you know, we only have 20 examples, but at least we don't have this strange behavior because we used our prior knowledge on the problem. Okay, here the same. Much better than the unconstrained solution. So another way, so this was one way that to validate a classifier. Already, it's a very strong tool. Essentially, when in many cases when we train a classifier, this is the first thing we do. We go and we look, we visualize the models, and we look and we try to see whether they make sense. But even if each one of these models makes sense, we still want to be able to tell if the overall classifier also gives reasonable results and whether it's robust. And we would like to think that we can get robustness by using a lot of independent features, a lot of independent sources of data. But what happens if we have, like, say, 20 features, but there are one or two strong features that basically determine the output of the classifier? Doesn't matter what the other features say, they determine the output of the classifier. And this is the role of veto analysis. We want to detect small subsets of features that have a veto privilege over the decision of the classifier. So a negative veto set is a subset of features that, by giving their lowest scores, can prevent positive classification regardless of what the other feature scores are. So this is a way to visualize it. There are two features here, and they push the classification toward the negative class, and it doesn't matter what the other features say. You can put all of them on this side of the scale. The scale will still tip to the right side. So we want to avoid small veto sets. Here's an example for the Titanic data set. I'll skip that because I don't have much time. Another tool that we use in validating classifiers is to get explanations. And the ability to explain a classifier, the decisions made by classifiers, first, it's a very strong validation tool. And after the classifier is deployed, and even during development, it's a very useful tool in investigating failures. So what's an explanation? An explanation for an instance classified as positive, an explanation is a minimal subset of in-favor features required to tip the scale in favor of the positive class against all against features, right? So some features give a good score, some features give a bad score. We put on one side of the scale all the features giving us bad scores, scores that push us below the threshold, and then we start adding features that increase the score to the other side. And when the scale tips, we call this set of features the explanation. So this is an explanation to, you can see it's a third-class passenger, adult, a female adult third-class passenger, and the classifier classified it to the positive class, and the explanation is that because it was a female. Okay, so that looks reasonable for this instance. And we can also provide group explanations. Basically, we explain each individual, and then we provide a summary of the explanations to this group. And a group of special interest is the group of misclassified examples, right? We want to know why misclassified examples were misclassified. So here's, again, the example for the Titanic. These are the misclassified negative examples. So these were examples that were, these are false positives. They were non-survivors that the classifier classified them as positive, as survivors. And the explanation that it gives to all of them is that they were females, right? So this is reasonable. The classifier saw that they were females, and they thought that they should have survived. On the complementary set is the misclassified positive examples, and here there are two explanations. One is that they were crew members, right? These were people who survived, but the classifier thought that they shouldn't have survived. So these were either crew members that survived or males that survives. Right, so let me just wrap up. So this is our revised machine learning workflow. The boldface parts are the parts that we think should be added for mission-critical applications. So choose and constrain the classifier and then train it. Visualization is very important in validating it. Veto analysis is important. Explanations are important. And after you deploy the classifier, it's also very important to explain the classifier's decisions. Thank you.